In this video we're going to be making a 360-degree ultrasonic distance visual in Python by using two 180-degree servo motors, an Arduino, a breadboard, an ultrasonic sensor, a few wires, cardboard and a glue gun. Let's begin. First, connect your Arduino to your computer and upload ExpressFormata onto it. This will allow us to connect to the ultrasonic sensor over Python, then unplug your Arduino. Now connect the 5-volt pin to the positive bus of the breadboard and the ground pin to the ground bus. On your servo motors there should be 3 wires. For both servos, connect the brown wire to the ground bus of your breadboard, the red wire to the positive bus. Then connect the yellow wire on one of the servos to pin 9, and the yellow wire on the second servo motor to pin 10. Your ultrasonic sensor should have 4 pins. Connect the VCC to the positive bus on the breadboard, connect the trigger pin to pin 3 of the Arduino, connect the echo pin to pin 2 of the Arduino, and finally, the ground pin to the ground bus of your breadboard. This completes the circuitry. Let's now create some Python code to reset the position of the servos. In idle, from pymata4, import pymata4. Then let's declare our board and the pins that we want it to access, which are pins 3 for the trig pin, 2 for the echo, and 9 and 10 for the servo motors. Then let's set the pin mode for the servo motors as servo pins, as well as setting their starting rotation as 0. For the ultrasonic sensor, set the pin mode for trig and echo to Sonar and call a function called distanceFunc. We can then create this function just above the set pin statement. First, create a variable called distance and set it to 0, then create a function called distanceFunc and pass through data. Data comes from the set pin mode to Sonar statement. Include the global variable distance, then set it to data2, which is the distance measure in centimeters. Now if we connect our Arduino to our PC and run the code, we will see that the servo motor's position is set to 0. Now that we've reset the position, unplug your Arduino. We then want to use a glue gun and glue one servo on top of the other. This will allow us to go from 180 degrees of movement control to 360 degrees by using both servos. Also glue your ultrasonic sensor to the top servo, then glue the bottom servo to a surface for stability. Now back in the code we can create the 360-degree rotation formula. Import time, then create 2 new variables that we will use to store the value of rotation in, and create a new function called servo control and reference those global variables. Create a while loop and add a time sleep of 0.1 seconds between each loop. For each servo rotation, we need to check if the value is over 180 degrees or not. If it is, then reset the value of rotation to 0, and set the servos to 0 degrees. If the value of rotation is not over 180, then set the servo position to rotation 2's value, and add 1 to the value of rotation 2. This will mean that the value in rotation 2 gets increased every loop until it reaches 181, then it gets reset to 0. Write a similar else statement for rotation 1. Then call the function to test it, and run the code. You will now see that when the first servo motor reaches 180 degrees, the second motor starts to turn. Once the second motor reaches 180 degrees, their combined value is 360 degrees and the rotation for both servo motors gets reset to 0 degrees. This is an endless loop that achieves a 0 to 360 degree rotation. Let's now build a user interface to view the distance measurements. Start by importing a few more libraries. We will need to import tkinter as tk, and import all from it. We also need the math and threading libraries. Start by creating a basic tkinter window with the title of 360-degree ultrasonic sensor, which has a black background, and is set to open in a zoomed state, which is full screen. Then scroll down to the bottom of the code and close the window main loop. We can get rid of the function call to servo control as we will use threading for this later. Run the code and we should see a basic black screen. That's great. Now let's create a canvas which we can draw shapes onto. Set the background to black and make it expand to fill the window area. Let's then create a few variables to get the current window width and height resolutions. We also need a slider, so that when the distance pings are placed on the screen, we can zoom in or out to increase or decrease the area covered by our visual. This will mean if we have objects close to the sensor, we can zoom in to get a more precise view of distance. Set the slider scale from -1 to -100. And set its default value to -15, then place it on the screen and run the code. Here we can see a slider has been created which we will use later on. Let's now create a few variables. We need a variable that combines rotation 1 and 2, as we need to work out the current rotation based on a 360-degree maximum. We also need to create a start width and height which we can use to place things in the middle of the screen. We also need a label to display the current ultrasonic sensor distance to the screen. Let's improve our interface and create a grid for our background. We want to place the grid lines at 4% of the screen resolution apart. So create a new variable called multiple, that is the distance of height times 4. We need to draw a lot of lines, so create a for loop with the range of 50. The horizontal lines need to be placed at the full width of the screen. The height of the placement will need changing on each loop. So for now make the height equal to height plus the multiple variable. The vertical lines will need the width changing every loop, so again, base this on the width plus the multiple variable. Then for each loop, we can increase the value of multiple by adding 4% of the screen resolution to it. This will place both vertical and horizontal lines 4% apart. We now need to create an oval for our distance pings to be placed on. Let's create a few variables. We need a size variable which we will set to 380. And an line width variable which we will set to 3 for now. Start another for loop with a range of 4 and create an oval which is based on the center point of the screen, minus and plus our size variable. This will create an oval 380 pixels away from the center of our screen in every direction. On each iteration of the loop, -80 from the size variable, this will make a smaller circle for each loop. Also set the value of line width to 1 as we want the inner lines to be thinner than the outer line. Let's also create a few lines that are drawn across our circle to signify degrees. Create a new variable called rotate, then start another for loop with a range of 8. Then create two variables, one for end width and end height, which we can use to place the end of our lines around the circle. We can use the math sin and cos functions and pass through the value of our rotation. So for the first line in the loop, the line will start at the center of the screen and end at 0 degrees. With a line width of 35% of the screen resolution, which is to the top of our first oval. For each loop add 45 to the rotation so that each line is drawn in 45-degree increments. If we then run our code, we will see we now have a grid drawn on the background, a distance label, and a Sonar oval screen which has inner ovals and lines placed within it. All is working so far. Now let's create a function to have a moving line based on the servo's 360-degree location, and display it on the screen. Declare a few global variables, then create a while true loop. As we did before when placing lines on an oval, we need to define the line endpoints. These are based on the line length, the line start which is the center of the screen, and the current rotation which is the servo position. With these variables we can use the createLine method to draw the line at the current rotation. To get a trailing line effect, we can use the after method and call a deleteLine function, which we need to create later, which will delete each drawn line after a short duration. On each loop we also need to update the variable current location with the new servo location and add a time sleep between each loop. Then we can create a delete line function which deletes the line. Next, let's create a function that draws a ping on the screen based on the location from our ultrasonic sensor. Declare a few global variables again, then create a while true loop. When we move our slider, we want the ping locations to be updated based on the slider scale, so we need to base the distance from the center of the screen to the outer edge of the radar oval on the scale of the slider by creating a variable called recalculated distance, which is the distance times the current slider value. Again, we need to use the sin and cos functions to create oval pings based on the servo's current rotation, and then draw a ping on the screen which is 10 pixels wide. We also want the pings to be deleted after a set time, so use the after method and call a function called delete ping which we haven't created yet. We need to save the current distance value for each ping, as the distance value is normally reset globally every loop and we don't want historically placed pings to update based on this. So we can create a new variable called distance value to store the current distance of the placed ping. Next, let's create an update location variable for when we need to update the location of the ping based on new slider values. Again, declare a few global variables and start a while true loop. Now set the value of recalculated distance to include the specific ping's distance value times by the new scale slider value. Each ping will have its own distance value saved when it's created, which gets stored until the ping is deleted. Then use the same ping end width and height formulas to calculate the placement, and use the canvas coordinates method to update its current location. Add a time sleep between each loop. We then need to create another function which calls the update location function and passes through the values from the update ping function. We can then start a thread to call the call update function so that it runs in parallel to the rest of the code for each ping created. We also need to update our distance label with the current distance and add a time sleep. Then let's create the delete ping function which deletes the current instance of the distance ping. The final thing we need to do is call all our functions by creating new threads for them so that the line rotation, the pings, and the servo controls can all run at the same time. Once this is done, we can run the code and see our software in action. Here we can see that the distance is accurately plotted on our screen, and the rotation aligns with our servo rotation. Using the scale slider allows us to redefine our scale range and either zoom in or out to get a greater or lower detailed view. The distance ping locations automatically update based on the new slider scale thanks to each one running its own thread and keeping its own relative distance for the life of the ping. With this setup, the servo completes a full 360-degree rotation before a ping is deleted. Currently, the ultrasonic sensor is obstructed by some wires. We can add a little arm to the sensor to move the wires out of the way on rotation using either some cardboard or tape. With the tape arm added, the wires are now moved out of the way. This isn't the most elegant solution, but it does the job. Now we have an uninterrupted 360-degree rotation. There are a lot of improvements that could be made to this project, such as better wire management, and a case to contain all the components so that they aren't free to move around. But hopefully this gets you started with creating a 360-degree visualization of the ultrasonic sensor in Python. Thanks for watching.